Hello there, and welcome to the Sleepless Scientist. Tonight, we're going on a journey through deep time, a voyage into the very bones of our planet. We'll explore the stories written in stone, the forces that shape continents, and the slow, patient processes that have been unfolding for billions of years beneath our feet. Geology is the art of reading Earth's autobiography, page by ancient page. It's a tale of fire and ice, of mountains rising and falling, of oceans opening and closing, like the breath of a sleeping giant. So settle in, let your mind wander through epochs and eons, and let the quiet wonder of Earth's history carry you toward rest. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time. The story written in stone. Every rock you've ever held carries a secret, a memory frozen in mineral form, waiting to be read. Some stones remember volcanic fury. Others recall the gentle accumulation of sand on ancient seafloors. The discipline of geology is essentially the practice of translation, learning to decode the language that Earth has been speaking for 4.5 billion years. It's not a language of words, but of textures and layers, of crystals and cracks, of the arrangement of atoms locked into place by unimaginable forces. When geologists examine a cliff face, they're not just seeing rock, they're seeing chapters of history stacked one atop another. A band of limestone might whisper of tropical seas that once covered what is now desert. A layer of volcanic ash marks a day of catastrophe, preserved forever. The story written in stone is patient. It doesn't rush. It waits for those curious enough to listen, to piece together the narrative of a planet that is very much alive, constantly rewriting itself in the slowest of motions. Tonight we begin to read that story together. The birth of a planet. Go back far enough, and there was no Earth at all, just a swirling disk of dust and gas orbiting a young, temperamental star. About 4.6 billion years ago, gravity began its patient work, pulling together grains of cosmic debris. Small clumps attracted more material, growing like snowballs rolling downhill. These planetesimals, as they're called, collided and merged in a chaotic dance of creation and destruction. With each impact came heat, tremendous world-melting heat. The young Earth was nothing like the blue marble we know today. It was a hellscape of molten rock, constantly bombarded by asteroids and comets. There were no oceans, no atmosphere to speak of, no life, just fire and fury. And yet, within that chaos, the seeds of everything we know were being planted. Iron and nickel sank toward the center, forming what would become the core. Lighter materials floated upward. The planet was sorting itself, layer by layer, density by density. It would take hundreds of millions of years for the bombardment to ease, for the surface to cool enough to solidify. But even in that violent beginning, the fundamental architecture of our world was taking shape. The molten beginnings of Earth. Picture a globe of liquid rock, glowing red and orange against the darkness of space. This was Earth in its infancy. A magma ocean, hundreds of kilometers deep, heated by the constant rain of impacts and the decay of radioactive elements within. The temperatures were staggering, hot enough to vaporize stone. Any water delivered by comets simply boiled away into space. The atmosphere, such as it was, consisted of rock vapor and superheated gases. There were no solid surfaces, no stable ground. Everything churned and roiled in a slow, viscous convection. Heat from the interior rose to the surface, radiated into space, then sank again to be reheated. This wasn't a place where anything could stand or grow or persist. It was a crucible, a forge, where the raw materials of a planet were being processed and refined. Yet even in this molten state, differentiation continued. Dense materials sank, light materials rose, and gradually, very gradually, the Earth began to organize itself into distinct layers. The magma ocean wouldn't last forever. Eventually, the bombardment would slow, the heat would dissipate, and the first thin skin of solid rock would form on the surface. The cooling of the young world. Slowly, so slowly, the inferno cooled. Heat radiated into the void of space, and with no constant replenishment from impacts, the surface temperature began to drop. The magma ocean, once a roiling globe of liquid stone, started to crystallize. The first minerals formed, tiny grains suspended in the melt, then settling, accumulating, building the foundation of what would become the crust. This wasn't a quick process. It took tens of millions of years for the surface to cool enough to form a stable, solid layer. Even then, the crust was fragile, easily broken and remelted by volcanic activity from below. The young Earth was still restless, still finding its equilibrium. But cooling brought something else, the possibility of water. Comets and asteroids continued to arrive, but now instead of vaporizing instantly, some of their ice could survive. Water vapor accumulated in the atmosphere, thick clouds forming for the first time, and eventually, when the surface was cool enough, it happened. Rain, not a gentle shower, but a deluge that may have lasted for millions of years, filling the first ocean basins and transforming Earth forever. The planet was no longer just fire. Now it held the promise of something more. The formation of the first crust. That first solid skin of rock was nothing like the continents we walk on today. It was thin, dense, and dark, composed primarily of basaltic minerals, rich in iron and magnesium. Think of it as a proto-crust, constantly recycled back into the mantle by the vigorous convection currents below. The early Earth had no stable land masses, no mountains, no valleys, just a shifting mosaic of volcanic rock, forming and reforming. But over time, something remarkable happened. Through repeated cycles of melting and crystallization, lighter minerals began to concentrate near the surface. Silica-rich rocks formed, less dense than basalt, and these couldn't sink as easily back into the mantle. They persisted. They accumulated. These were the seeds of the continents, small patches of buoyant crust that resisted recycling. Geologists call these ancient fragments cratons, and they're still with us today, buried at the hearts of our modern continents. The oldest rocks ever found, in places like Canada and Western Australia, date back over 4 billion years. They're survivors from a time when the Earth was still finding its form, still experimenting with stability. That first crust was the beginning of the solid world we inhabit. The planet's layers beneath us. Stand anywhere on Earth, and you're perched atop an intricate structure of nested spheres. Beneath your feet lies the crust, a thin shell of solid rock that varies from just 5 kilometers thick under the oceans to 70 kilometers beneath mountain ranges. It's barely a fraction of the planet's radius, yet it's the only layer we've directly sampled. Below the crust sits the mantle, a vast region of hot, slowly flowing rock that extends nearly 3,000 kilometers down. Though solid, it behaves like a fluid over geological timescales, churning in convection currents that drive the movement of continents. Deeper still lies the outer core, a sea of liquid iron and nickel, where temperatures reach 5,000 degrees Celsius. This molten layer generates Earth's magnetic field through its constant motion, and at the very center, under crushing pressure, sits the inner core, a solid sphere of iron, somehow crystallized despite the heat, compressed by the weight of the entire planet above it. Each layer formed through differentiation, with density determining depth. Together, they create a dynamic system where heat from the interior constantly seeks escape, driving all the geological processes we see at the surface. The structure of the Earth's core, the core of our planet, is a realm of extremes we'll never visit. It begins about 3,000 kilometers below the surface, where temperatures soar and pressures become almost incomprehensible. The outer core is liquid, a churning ocean of molten iron and nickel, heated by residual warmth from Earth's formation and by the decay of radioactive elements. This liquid metal, flows in complex patterns, driven by convection and twisted by the planet's rotation. These motions generate electrical currents, which in turn create the magnetic field that shields our surface from solar radiation. Without this invisible bubble, life as we know it couldn't exist. Even deeper, at 5,000 kilometers down, lies the inner core, a solid sphere roughly the size of the moon. Despite temperatures that exceed the surface of the sun, the immense pressure at this depth forces iron atoms into a crystalline structure. The inner core rotates slightly faster than the rest of the planet, a discovery made by studying how seismic waves travel through it. It's a world within a world, utterly alien, yet fundamentally connected to everything above. The core is Earth's engine, the source of the energy that keeps our planet geologically alive, the mantle that moves continents. Between the core and the crust lies the mantle, a region so vast it contains 84% of Earth's volume. It's made primarily of silicate minerals rich in iron and magnesium, compressed under tremendous pressure and heated to over 3,000 degrees Celsius near its base. Despite these conditions, the mantle isn't liquid. It's solid rock, but on geological timescales, it flows. Imagine honey or glass, substances that seem solid but can deform slowly under stress. The mantle behaves similarly, creeping at rates of a few centimeters per year. Heat from the core warms the deepest mantle, causing it to expand slightly and rise toward the surface. As it rises, it cools, eventually sinking back down to be reheated. These convection currents, operating over millions of years, are the engine behind plate tectonics. Hot mantle rising beneath mid-ocean ridges pushes plates apart. Cool, dense mantle sinking pulls plates down at subduction zones. The crust is merely a passenger, carried along by these deeper currents. Everything we see at the surface, earthquakes, volcanoes, mountain building, is ultimately driven by the slow, patient churning of the mantle below. It's the great conveyor belt of our planet, endlessly recycling rock and redistributing heat. The shifting of the tectonic plates. The Earth's crust isn't a single, unbroken shell. It's fractured into about a dozen major plates and many smaller ones, all slowly drifting across the surface. These plates carry continents and ocean floors, grinding past each other, colliding, or pulling apart. The theory of plate tectonics, fully accepted only in the 1960s, revolutionized our understanding of the planet. Suddenly, geology made sense as a unified system. Earthquakes occurred, where plates scraped together. Volcanoes formed, where one plate dove beneath another. Mountain ranges rose, where continents collided. At mid-ocean ridges, plates diverge, and new crust forms from upwelling magma. At subduction zones, old oceanic crust plunges back into the mantle, melting and recycling. Transform boundaries. Let plates slide horizontally past each other, storing stress until it's released in violent tremors. The speeds are modest, about as fast as your fingernails grow. But over millions of years, these tiny motions add up to enormous changes. Oceans open and close. Supercontinents form and fragment. The map of Earth is constantly being redrawn, slowly but surely, by the restless dance of the plates. It's a planetary-scale ballet choreographed by heat and gravity. The great puzzle of Pangaea. About 300 million years ago, all of Earth's landmasses were joined in a single supercontinent. Geologists call it Pangaea, meaning all Earth. If you could stand on its shores, you'd see every modern continent locked together like pieces of a jigsaw puzzle. Africa fits snugly against South America. North America nestled beside Europe and Northern Africa. India was tucked under Asia. Antarctica and Australia completed the assembly. The evidence for Pangaea is compelling. Matching rock formations appear on now distant continents, as if torn from the same geological fabric. Fossils of identical species are found on opposite sides of oceans, creatures that couldn't possibly have crossed such barriers. Ancient mountain ranges align perfectly when continents are reassembled. Even glacial deposits tell the story, showing ice sheets that only make sense if the land masses were positioned differently. Pangaea wasn't Earth's first supercontinent, nor its last. The planet cycles through these assemblies roughly every 500 million years, with continents drifting together, staying merged for a time, then fragmenting again. Pangaea began breaking apart about 200 million years ago, rifting first along what would become the Atlantic Ocean. The pieces have been drifting ever since, slowly approaching their next configuration. The slow dance of continents. Continental drift happens so gradually that in a human lifetime, you'd never notice. Yet measured over millions of years, the motion is undeniable. South America and Africa, once joined, now sit separated by thousands of kilometers of Atlantic seafloor. India, once an island continent, crashed into Asia with such force it crumpled the crust upward, creating the Himalayas. Australia is sliding northward, closing the gap with Southeast Asia. Even now, the continents continue their patient journey. The Atlantic widens by a few centimeters each year as new crust forms at the mid-Atlantic ridge. The Pacific shrinks as its edges are consumed in subduction zones around the Ring of Fire. In about 50 million years, if the motion continues, Africa will collide with Europe, sealing the Mediterranean Sea and raising a new mountain chain. Australia will merge with Asia. The Americas may begin drifting westward at different rates, opening new seaways. This dance has been going on for billions of years, reshaping the planet's surface again and again. Every coastline is temporary, every ocean basin a fleeting feature in geological time. The solid ground beneath us is anything but static. The creation of mountains. Mountains are born from collision and compression. When tectonic plates converge, something has to give. If both plates carry continental crust, relatively light and buoyant, neither can easily sink into the mantle. Instead, they crumple. Rock layers fold like fabric pushed together on a table. Thrust faults form as massive slabs of crust override one another, stacking kilometers thick. The surface buckles upward, rising against gravity. This is how the great mountain ranges form. The Himalayas, the Alps, the Rockies. The process is violent on a geological scale, though imperceptibly slow by human standards. Over millions of years, sedimentary rocks that once lay flat on ancient seafloors are tilted vertical, folded into impossible curves, and lifted thousands of meters into the sky. You can find marine fossils at the summit of Everest, a testament to just how much the crust has moved. Not all mountains form through collision. Volcanic mountains build from below, as magma forces its way to the surface and accumulates in layers of hardened lava. But the tallest, most dramatic ranges are those carved by tectonic forces, where the clash of continents thrusts the Earth's skin skyward, creating peaks that scrape the atmosphere. The power of colliding plates. When plates collide, the energy released is staggering. The forces involved can fold solid rock like putty, break it along, faults spanning hundreds of kilometers, or melt it entirely through friction and pressure. At convergent boundaries, where plates meet head-on, the outcome depends on what type of crust they carry. If an oceanic plate meets a continental plate, the denser oceanic crust typically subducts, diving beneath the continent and descending into the mantle. This creates deep ocean trenches and chains of volcanoes on the overriding plate. If two oceanic plates collide, one subducts beneath the other, forming volcanic island arcs. But when two continental plates meet, neither wants to subduct. Instead, they collide and compress, thickening the crust and building mountains. The Himalayas are the result of India's ongoing collision with Asia, a crash that began 50 million years ago and continues today. The collision zone stores immense stress, released periodically in devastating earthquakes. These boundaries are among the most geologically active places on Earth, where the planet's restless energy finds dramatic expression. Every collision tells a story of motion and force, of rock responding to pressures beyond human comprehension. The rise of the Himalayas. 50 million years ago, India was an island continent racing northward across the ancient Tethys Sea at a breakneck pace, geologically speaking, of about 15 centimeters per year. When it slammed into Asia, the collision began building what would become the world's tallest mountain range. The Himalayas aren't finished growing. Even now, they continue rising about 5 millimeters annually as India pushes relentlessly into Asia. The sheer scale of the collision is astonishing. The crust in this region has doubled in thickness, creating a plateau, the Tibetan Plateau, that stands kilometers above sea level. Rock layers have been folded, faulted, and stacked in incredibly complex patterns. Metamorphic rocks formed deep underground have been thrust upward and exposed at the surface. The range includes 14 peaks over 8,000 meters tall, crowned by Mount Everest at 8,849 meters. But the Himalayas are more than just tall mountains. They alter weather patterns, creating the monsoon system that sustains billions of people. They store vast amounts of ice, feeding rivers that water much of Asia. And they're a natural laboratory for studying mountain building, offering insights into the forces that shape our planet's surface, the erosion that wears them down. The moment a mountain rises, erosion begins its patient work of tearing it down. Water is the primary sculptor. Rain falls, seeps into cracks, freezes and expands, breaking rock apart grain by grain. Rivers carve channels down mountainsides, carrying sediment toward the sea. The higher the mountain, the more dramatic the erosion, as steep slopes and heavy precipitation accelerate the process. Wind scours exposed peaks, blasting them with ice and sand. Chemical weathering dissolves minerals, weakening the rock's structure. Even living things contribute. Plant roots pry open fissures. Microbes produce acids that dissolve stone. The Himalayas are eroding even as they rise, with estimates suggesting the net growth is only about 3 millimeters per year. Rivers like the Ganges and Brahmaputra carry away enormous quantities of sediment, material that once stood as mountain peaks now deposited across vast floodplains or swept into the ocean. Over geological time, erosion always wins. Every mountain range ever built has eventually been worn flat, reduced to gentle plains. The Appalachians, once potentially as tall as the Himalayas, now stand as mere remnants. Erosion is geology's great equalizer, endlessly recycling the rock at the surface. The cycle of uplift and decay. Mountains rise and fall in a rhythm as fundamental as breathing. Tectonic forces push the crust upward. Collisions build ranges. Volcanic activity creates peaks. But immediately, erosion begins the work of removal. Rock fragments tumble downslope, accumulate in valleys, wash into rivers. This sediment is carried to lowlands, or the sea, where it settles in layers. Buried under more sediment, compressed and cemented, it becomes new rock. Millions of years later, tectonic shifts might lift these sedimentary layers, exposing them to erosion once more. The cycle continues. Material from the high places flows to the low places. What was once mountain becomes seafloor. What was seafloor becomes mountain. The rock doesn't disappear. It transforms and travels. Geologists see this cycle everywhere they look. Sedimentary rocks high in mountains contain fossils of marine creatures. Metamorphic rocks at the surface were once buried kilometers deep. The timescales are vast, spanning hundreds of millions of years. But the process is continuous and inevitable. Uplift provides the material. Erosion redistributes it. Gravity drives the flow, and the planet slowly recycles its outer layer, creating new landscapes from the ruins of old ones. The rock cycle that never ends. Imagine rock, not as permanent, but as a temporary state in an endless transformation. The rock cycle describes how material moves between three basic forms: igneous, sedimentary, and metamorphic, driven by heat, pressure, and time. Begin with magma rising from the mantle. When it cools and solidifies, it becomes igneous rock. Exposed at the surface, it weathers and breaks into fragments. These pieces are transported by water, wind, or ice, and deposited as sediment, buried under layers of more sediment, compressed and cemented over millions of years. They become sedimentary rock. Push this rock deep enough, through subduction or continental collision, and heat and pressure transform it into metamorphic rock. Heat it further, and it melts, becoming magma once more. The cycle completes, ready to begin again. But the paths aren't fixed. Igneous rock can melt back into magma without ever becoming sedimentary. Metamorphic rock can be uplifted and eroded directly. Sedimentary rock can be metamorphosed, then melted. The cycle has countless variations, every rock following its own journey through Earth's interior and surface. Nothing is permanent. Everything is in motion, cycling through states on timescales that dwarf human civilization. The three families of stone. All rocks on Earth belong to one of three categories, each with its own origin story. Igneous rocks form from cooled magma or lava. Molten rocks solidified into minerals. They're the primary rocks, created directly from Earth's interior. Sedimentary rocks are secondary, formed from accumulated fragments of other rocks, or from chemical precipitation. They're the records keepers, preserving layers of time and fossils of ancient life. Metamorphic rocks are rocks that have been changed, transformed by heat and pressure. While remaining solid, their minerals reorganized into new patterns. Each family has distinctive characteristics. Igneous rocks often show interlocking crystals where minerals grew together as the melt cooled. Sedimentary rocks display layers and may contain fossils or rounded grains from transport. Metamorphic rocks frequently show foliation, parallel alignment of minerals or larger crystals formed during transformation. By examining a rock's texture and composition, geologists can determine its family and reconstruct its history. Was it born from volcanic fire? Did it accumulate slowly in an ancient sea? Was it buried deep and transformed by tectonic forces? Every rock tells a story if you know how to read it. These three families encompass all the stone you'll ever encounter. The igneous rocks, born from fire. Igneous rocks begin as magma, molten rock beneath Earth's surface, formed when pressure drops or water lowers the melting point of the mantle or crust. When magma reaches the surface through volcanic eruptions, it becomes lava, cooling quickly in contact with air or water. This rapid cooling creates fine-grained rocks like basalt, where crystals don't have time to grow large. The dark volcanic rocks of Hawaii and Iceland are basaltic, rich in iron and magnesium. When magma doesn't reach the surface but cools slowly underground, the crystals have time to grow, forming coarse-grained rocks like granite. These intrusive igneous rocks may cool over thousands or millions of years, developing large, interlocking crystals visible to the naked eye. Eventually, erosion removes the overlying rock, exposing these once-buried formations. Granite forms the cores of many mountain ranges and continental shields. The composition of igneous rocks varies based on their source. Magma from the mantle tends to be basaltic, while magma generated from melted continental crust is more silica-rich, forming granite or its volcanic equivalent, rhyolite. Igneous rocks are direct samples from Earth's interior, frozen moments in the planet's thermal history. They form the foundation of geology itself. The sedimentary rocks of time. Sedimentary rocks are the archives of Earth's surface processes, formed from accumulated fragments or chemical precipitates. The process begins with weathering, rock breaking down into smaller pieces through physical and chemical means. These fragments, sand, silt, clay, are transported by water, wind, or ice, and eventually deposited in layers. Over time, burial under more sediment compresses the lower layers. Minerals precipitating from groundwater cement the grains together, transforming loose sediment into solid rock. Sandstone forms from ancient beaches or dunes. Shale forms from compressed mud at the bottom of quiet waters. Limestone often forms from the accumulated shells and skeletons of marine organisms. A rock made almost entirely of biological material. Sedimentary rocks are layered, with each layer representing a period of deposition. They're time capsules, preserving fossils, ancient climate indicators, and evidence of past environments. A layer of coal might mark an ancient swamp forest. Salt deposits indicate evaporated seas. Red sandstone suggests desert conditions. By reading these layers like pages in a book, geologists reconstruct Earth's history, the rise and fall of oceans, the advance and retreat of glaciers, the evolution of life itself. Sedimentary rocks make up only 5% of the crust by volume, but they cover 75% of the land surface, draping over older rocks like a historical record. The metamorphic rocks of change. Metamorphic rocks are rocks reborn, transformed by heat, pressure, or chemically active fluids, while remaining solid. The word metamorphic literally means changed form. Take a sedimentary shale, bury it 20 kilometers deep beneath a growing mountain range, subject it to temperatures of 500 degrees Celsius and pressures thousands of times atmospheric, and it becomes schist, a rock with entirely different mineral composition and structure. The transformation happens slowly, over millions of years, as atoms migrate and reorganize without the rock melting. Limestone metamorphoses into marble, its calcite crystals growing larger and interlocking. Sandstone becomes quartzite, its quartz grains fusing into a harder, denser rock. Granite transforms into gneiss, developing distinctive banding as minerals separate into light and dark layers. Metamorphic rocks often form at tectonic plate boundaries, where collisions bury rock deep, or near magma intrusions, where heat from below transforms surrounding rock. They tell stories of mountain building and continental collisions. The presence of certain metamorphic minerals indicates specific temperature and pressure conditions, allowing geologists to calculate how deeply rocks were buried and how hot they became. Metamorphic rocks are common in ancient mountain cores and in exposed fragments of deep crust brought to the surface. They're evidence of the extreme conditions that exist just kilometers beneath our feet. The hidden history in layers. Look at any cliff face displaying sedimentary rock, and you're seeing a timeline stretching into the deep past. Each layer, or stratum, represents a period of deposition. The principle is simple. In an undisturbed sequence, older layers sit beneath younger ones. This concept, called superposition, is fundamental to geology, but reading the layers requires more than just counting them. Variations in thickness, grain size, and composition reveal changing conditions. A thick layer of coarse sandstone might indicate a period of strong currents. A thin band of clay suggests quiet water. The presence of certain minerals hints at the climate when the sediment was deposited. Gaps in the sequence, called unconformities, mark periods when erosion removed rock or deposition stopped. These gaps can represent millions of years of missing history. Folding and faulting can complicate the picture, tilting layers vertical or even overturning them entirely. Geologists become detectives, piecing together evidence from multiple locations to reconstruct ancient environments. Was this a river delta, a shallow sea, a desert dune field? The layers hold the answers, written in patterns of grain and color, preserved across vast spans of time. Every cliff is a library, every outcrop a chapter, the story told by fossils. Within sedimentary layers lies evidence of ancient life, fossils, the preserved remains or traces of organisms. When a creature dies and is quickly buried by sediment, conditions may prevent decay. Over time, minerals replace organic material, creating a stone replica. Hard parts like shells, bones, and teeth fossilize most readily, but even soft tissues can be preserved under exceptional circumstances. Fossils tell us not only what lived long ago, but also how ecosystems evolved over time. They reveal when major groups of organisms appeared and disappeared. The fossil record shows a progression: simple life in ancient rocks, increasing complexity in younger ones. Mass extinctions appear as sudden disappearances of many species, followed by radiations as new groups diversified. Fossils also help correlate rock layers across vast distances. If the same distinctive fossil appears in layers on different continents, those layers are roughly the same age. Index fossils from organisms that lived briefly but spread widely are particularly useful for dating rocks. Beyond their scientific value, fossils connect us viscerally to deep time. Hold a trilobite, and you're touching something that crawled across the seafloor 500 million years ago. The stone remembers. The past is not gone. It's transformed, waiting to be discovered. The preservation of ancient life. Fossilization is rare. Most organisms decay completely, returning their atoms to the cycle of life, but occasionally, conditions align to preserve remains for millions of years. Quick burial is essential. It protects the remains from scavengers and slows decay. Fine sediment, like mud, preserves more detail than coarse sand. Low oxygen environments inhibit decomposition. Over time, minerals dissolved in groundwater percolate through the buried remains. They precipitate in pore spaces, eventually replacing organic molecules atom by atom. The result is a rock replica of the original structure, often preserving astonishing detail. There are many types of preservation. Permineralization fills pores with minerals, while leaving some original material. Replacement substitutes minerals for the original structure entirely. Carbonization leaves only a carbon film outlining the organism. Molds and casts preserve the shape even when the original material dissolves. Trace fossils like footprints or burrows record behavior rather than bodies. Under extraordinary conditions, soft tissues, fur, or even color patterns can be preserved. Each fossil is a small miracle, a window into vanished worlds, proving that life on Earth is ancient beyond comprehension and has taken forms stranger than we might imagine. The record of extinction and renewal. The fossil record is punctuated by mass extinctions, sudden events when a significant percentage of Earth's species disappeared. The most famous, the Cretaceous-Paleogene extinction 66 million years ago, ended the reign of the dinosaurs. An asteroid impact and massive volcanic eruptions created conditions that most large land animals couldn't survive. But extinctions, while catastrophic, create opportunities. After each mass die-off, surviving lineages diversified rapidly to fill empty ecological niches. Mammals, previously small and insignificant, expanded after the dinosaurs vanished, eventually producing the diversity we see today. 5 major mass extinctions mark the geological record, each with different causes: climate change, volcanic eruptions, asteroid impacts, ocean chemistry shifts. Between these crises, smaller extinction events and the normal background extinction of species continue. Extinction is part of life's pattern. Species emerge, persist, and eventually disappear. The average lifespan of a species is just a few million years. What's remarkable is not extinction itself, but the resilience of life as a whole. After every catastrophe, ecosystems recover. New forms emerge. The story continues, written in the layers of stone. The power of volcanoes. Volcanoes are Earth's pressure relief valves, places where molten rock from the interior reaches the surface. They form primarily at plate boundaries, where plates diverge and new crust forms, or where one plate subducts beneath another, melting and generating magma. When pressure from dissolved gases becomes too great, eruptions occur. Lava flows stream down mountainsides, cooling into new rock. Explosive eruptions hurl ash and debris kilometers into the atmosphere, sometimes triggering global climate effects. The 1815 eruption of Mount Tambora in Indonesia ejected so much material it caused the year without a summer across the northern hemisphere. Yet volcanoes aren't just destructive. They create new land, building islands in the ocean and adding to continents. They recycle material from deep in the earth, bringing nutrients to the surface. Volcanic soil is remarkably fertile, which is why people often live near active volcanoes despite the risk. Throughout Earth's history, massive volcanic events called flood basalts have covered vast areas with lava, some eruptions lasting hundreds of thousands of years. These may have contributed to mass extinctions by releasing climate-altering gases. Volcanoes remind us that Earth's interior is hot and active, constantly reshaping the surface from below. The flow of lava and creation of land. When magma reaches the surface, it becomes lava, molten rock flowing across the landscape. The character of a lava flow depends on its composition and temperature. Basaltic lava, low in silica, is relatively fluid and can travel long distances, forming broad, shield-shaped volcanoes. Like those in Hawaii, it flows in rivers of glowing rock, cooling to form ropey surfaces called paho, or rough, jagged surfaces called More silica-rich lavas are thick and viscous, barely flowing before solidifying. These form steep-sided domes, or explosive eruptions, when gases can't escape easily. As lava cools, it contracts and often cracks in distinctive patterns. Columnar basalt formations, like those at Giant's Causeway in Northern Ireland, form perfect hexagonal columns through cooling fractures. Over repeated eruptions, layer upon layer of lava builds up, creating volcanic landforms. In some places, fissure eruptions pour lava from long cracks, rather than central vents, covering vast areas in sheets of basalt. The ocean floors are almost entirely basaltic lava, formed at mid-ocean ridges. Every grain of this rock was once molten, a reminder that the solid ground beneath us was once fluid, born from Earth's fiery depths. The islands formed by fire, volcanic islands, emerge from the seafloor, built entirely by repeated eruptions. Hawaii provides the classic example. A chain of islands formed as the Pacific Plate moved over a stationary hotspot in the mantle. Magma rises from deep below, erupts underwater, and gradually builds a mountain. Eventually, after thousands of eruptions, the volcano breaches the surface. More eruptions add height and width, creating an island. As the plate continues moving, it carries the volcano away from the hotspot. Cut off from its magma source, the volcano becomes extinct. Meanwhile, a new volcano begins forming over the hotspot, creating the next island in the chain. This process has built the entire Hawaiian island chain, with the Big Island currently over the hotspot and still growing, while older islands to the northwest are gradually eroding. Iceland formed differently, sitting directly on the mid-Atlantic ridge, where two plates diverge. Magma continuously rises from the mantle, creating new crust and feeding numerous volcanoes. The entire island is volcanic, built over millions of years. Other island chains, the Azores, the Galapagos, the Canaries, each tell similar stories of fire-building land from the sea. These islands are windows into processes occurring beneath the ocean everywhere. The deepest volcanoes beneath the sea, the most active volcanic zone on Earth, lies underwater, invisible to most of us. The mid-ocean ridge system, a continuous mountain range spanning 60,000 kilometers around the globe, is where new oceanic crust is born. Magma rises from the mantle through a rift valley at the ridge crest, erupting as underwater lava flows. Water pressure at these depths prevents explosive eruptions. Instead, lava oozes out, in characteristic pillow-shaped blobs that cool rapidly in contact with seawater. These pillow basalts blanket the seafloor, creating new crust that slowly spreads away from the ridge. The process is continuous. As plates diverge, more magma rises to fill the gap. Submersibles exploring these ridges have discovered entire ecosystems thriving around hydrothermal vents where superheated water charged with minerals erupts from the seafloor. These underwater volcanoes also occur at hotspots far from ridge systems, building seamounts, underwater mountains that never quite reach the surface. Tens of thousands of seamounts dot the ocean floors, most unknown and unmapped. Some grow large enough to become islands. Others remain submerged, slowly eroded by currents, and eventually carried by plate motion into subduction zones, where they're recycled back into the mantle. The ocean floor is young compared to continents. The oldest seafloor is only about 200 million years old, constantly created at ridges and destroyed at trenches. These hidden volcanoes, erupting in darkness and pressure, are fundamental to plate tectonics and the recycling of Earth's crust. The tremors of the Earth. Earthquakes are sudden releases of energy. As rock breaks or slips along faults, stress accumulates over years or centuries. As tectonic plates slowly grind against each other, rock can bend and deform elastically, but only to a point. When stress exceeds the rock's strength, it fractures. The stored elastic energy releases instantly, radiating outward as seismic waves that shake the ground. Most earthquakes occur at plate boundaries, where motion is concentrated, but they can happen anywhere. Stress builds in the crust. The magnitude measures the energy released, while intensity describes the shaking's effects at the surface. A magnitude 8 earthquake releases about 30 times more energy than a magnitude 7. Seismic waves come in types. P waves compress and expand rock, traveling fastest and arriving first. S waves shake rock perpendicular to their direction, arriving second. Surface waves travel along Earth's outer layer, causing most damage. By analyzing how these waves travel through the planet, seismologists have mapped Earth's interior structure, discovering layers we can never directly sample. Earthquakes are destructive, but also informative, revealing the planet's hidden architecture and the constant stress of tectonic motion. The mystery of earthquakes. Despite decades of study, earthquakes remain partly mysterious. We understand the mechanism, elastic rebound along faults, but predicting when and where they'll strike remains impossible. Faults are complex three-dimensional structures, not simple cracks. They branch, intersect, and have irregular surfaces. Some sections creep slowly and continuously, releasing stress gradually. Others lock for decades or centuries, then rupture catastrophically. Why certain sections behave differently isn't fully understood. Small earthquakes don't necessarily relieve stress. Sometimes they trigger larger ones. Foreshocks can precede major quakes, but there's no way to distinguish them from ordinary seismicity until after the big one hits. Statistical patterns exist. Aftershocks follow power laws, and earthquake frequency relates to magnitude predictably. But these describe populations, not individual events. Some researchers study precursor signals, changes in groundwater, animal behavior, electromagnetic anomalies, but nothing reliable has emerged. The best we can do is assess long-term probability. A fault that hasn't ruptured in centuries is more likely to do so soon. Building codes in seismic zones help mitigate damage. Early warning systems can provide seconds to minutes of notice, but earthquakes remain fundamentally unpredictable. Sudden reminders of the forces moving beneath our feet, the cracks that move continents. Faults are fractures in Earth's crust, where rock has moved. They range from tiny cracks to zones spanning hundreds of kilometers. Transform faults, where plates slide horizontally past each other, are particularly impressive. The San Andreas Fault in California is the most famous, marking the boundary between the Pacific and North American plates. The Pacific plate moves northward relative to North America at about 5 centimeters per year. Over millions of years, this motion adds up. Los Angeles, on the Pacific plate, is slowly approaching San Francisco. In about 15 million years, they'll be neighbors. But the motion isn't smooth. Friction locks the fault for decades, while stress builds. Suddenly the fault ruptures, releasing that stored stress in seconds. Rock on opposite sides of the fault can shift several meters instantly, producing major earthquakes. The 1906 San Francisco earthquake involved up to 6 meters of horizontal displacement. Not all transform faults are on land. Fracture zones in the ocean offset mid-ocean ridges, accommodating the spreading of new seafloor. These faults are fundamental to plate tectonics, allowing rigid plates to move across a spherical surface without gaps or overlaps. They're the seams in Earth's fractured shell, the San Andreas Fault and beyond. The San Andreas Fault stretches over 1,200 kilometers through California, from the Salton Sea to Cape Mendocino. It's not a single crack, but a zone of deformation up to a kilometer wide in places. Some sections creep continuously, while others remain locked. The locked sections store stress for decades or centuries before rupturing in major earthquakes. The southern section last ruptured in 1857, the northern section in 1906. The central section creeps steadily. Geologists study the fault intensely, digging trenches across it to find evidence of past earthquakes in offset layers. They've discovered that major quakes on the southern section repeat roughly every 150 years. The next big one is overdue by some estimates, though earthquake timing is irregular enough that overdue means little. Beyond California, other major transform faults exist. The North Anatolian Fault in Turkey has produced devastating earthquakes. The Alpine Fault in New Zealand accommodates motion between the Pacific and Australian plates. The Dead Sea Transform separates the Arabian and African plates. Each tells a story of continents moving, of plates grinding past each other, releasing energy that shakes cities and reshapes landscapes. These faults are active boundaries, constantly evolving, the shifting of time and stone. Geological time operates on scales that challenge human comprehension. 1,000,000 years, an almost unimaginable span to us, is brief in Earth's history. The planet is 4.6 billion years old. Life has existed for at least 3.5 billion years. Complex multicellular life emerged only about 600 million years ago. The dinosaurs ruled for 160 million years and had been gone for 66 million. Our species has existed for perhaps 300,000 years, and civilization for only 10,000. We are newcomers to a very old world. Yet in that immense span, rock has cycled repeatedly through creation, destruction, and transformation. Mountains have risen and eroded away multiple times. Continents have assembled into supercontinents and fragmented again several times over. Oceans have opened and closed. The rock we see at the surface may have been seafloor sediment, then metamorphosed deep underground, then uplifted and exposed, all over hundreds of millions of years. Time is geology's most essential ingredient. The slow processes we observe, erosion, sedimentation, plate motion, accumulate over eons into transformative change. Understanding geological time means accepting that the Earth we see is merely one frame in an enormously long film, constantly changing but too slowly for us to perceive directly. The science of minerals. Minerals are the building blocks of rocks, naturally occurring, inorganic solids with specific chemical compositions and ordered atomic structures. About 5,000 mineral species have been identified, though only a few dozen make up the vast majority of Earth's crust. Quartz, feldspars, micas, pyroxenes, amphiboles, and olivines dominate most rocks. Each mineral forms under specific conditions of temperature, pressure, and chemical environment, which makes them useful for reconstructing rock histories. Minerals aren't just useful scientifically, they're essential to civilization. We extract metals from ore minerals, manufacture electronics from rare earth elements, build with stone, use clay for ceramics, and prize certain minerals as gemstones. The atoms in minerals arrange themselves into orderly crystal structures, repeating patterns that determine their properties. Hardness, cleavage, color, and crystal shape all reflect internal atomic arrangement. Some minerals are stable across wide ranges of conditions, while others form only in very specific circumstances. High-pressure minerals from deep in the mantle occasionally appear at the surface, carried up by volcanic eruptions or exposed when ancient mountain roots erode. Each mineral has a story of where it formed, under what conditions, and how it traveled to reach us. The crystals that grow in darkness, deep beneath the surface, in cracks and cavities within cooling magma, or in spaces between rocks, crystals grow slowly, in complete darkness. Given time and space, minerals form perfect geometric shapes as atoms arrange themselves into ordered structures. A crystal growing in a fluid-filled cavity might take thousands of years to reach the size of your thumb, adding layer by atomic layer. The conditions must remain stable. Temperature, pressure, and chemical composition all influencing the outcome. Some of Earth's largest crystals grew in these hidden spaces. The Cave of Crystals in Naka, Mexico, contains selenite crystals up to 11 meters long and weighing 55 tons, grown over 500,000 years in a magma-heated chamber. Geodes, hollow rocks lined with crystals, form when mineral-rich fluids slowly deposit crystals on cavity walls. Crack open a geode, and you might find amethyst, calcite, or agate, structures of remarkable beauty created by patient geological processes. These crystals never saw light during their formation, growing in conditions of constant temperature and chemistry that allowed perfection. They're treasures from Earth's hidden interior, proof that spectacular beauty can emerge from simple chemical processes given time and stability. The beauty hidden in the Earth. Beneath unremarkable rock surfaces lie extraordinary treasures. Minerals form in astonishing variety. The deep purple of amethyst, the rich green of malachite, the metallic gold of pyrite, the translucent blue of celestite. Color comes from impurities, slight variations in chemistry that change how minerals interact with light. Crystal forms range from delicate needles to sturdy cubes, to complex geometric arrangements. Some minerals fluoresce under ultraviolet light, glowing in colors never visible in daylight. Others show optical effects, the play of color in opal, the star pattern in star sapphires, the shifting bands in tiger's eye. These aren't decorations added by nature for our appreciation. They're consequences of physics and chemistry, of atomic structures and light interactions. Yet we can't help but find them beautiful. Mineral collecting has been a human passion for millennia. Museums display spectacular specimens, but the real treasures are the ones you find yourself, splitting open a rock to reveal crystals inside, discovering the extraordinary hidden within the ordinary. Earth's interior is a gallery of natural art, created by processes that care nothing for aesthetics, yet produce works of stunning beauty. The planet makes masterpieces in darkness. The sparkle of quartz and diamond. Quartz is one of Earth's most common minerals, silicon and oxygen atoms, arranged in a framework that's remarkably stable. It appears in many forms. As clear rock crystal, it was once thought to be permanently frozen water. As purple amethyst or yellow citrine, it's valued for jewelry. As microscopic grains, it forms much of the world's sand. Quartz is hard, resistant to weathering, and chemically stable, which explains why it accumulates in sediments. Other minerals break down, while quartz persists. Diamond is rarer and more remarkable. Pure carbon atoms, arranged in the strongest atomic structure known, formed under extreme pressure, deep in the mantle, 150 kilometers or more beneath the surface. Diamonds reach the surface only through violent volcanic eruptions that blast through the crust at supersonic speeds, carrying fragments of mantle rock, including diamonds. Most diamonds are billions of years old, formed in Earth's deep past. Their hardness and light-dispersing properties make them prized as both gemstones and industrial tools. Yet chemically, a diamond is identical to graphite or coal, just carbon atoms arranged differently. The structure makes all the difference, transforming ordinary carbon into the hardest natural substance, a crystal that can sparkle for eternity. The rarity of gemstones. Most minerals are common and abundant. A few are precious, rare either because the conditions for their formation occur infrequently or because high-quality specimens are scarce. Emeralds require beryllium, chromium, and specific formation conditions rarely found together. Rubies and sapphires are corundum, aluminum oxide, colored by trace elements and formed at high temperatures. Most corundum is dull and industrial. Gem-quality specimens are exceptional. Value depends not just on rarity, but on human preferences, clarity, color intensity, size, and sometimes history. A stone's journey from deep in the earth to someone's hand involves geological luck and human effort. Most gemstones form deep underground, requiring uplift and erosion to bring them within reach. Some form in pegmatites, pockets of rare elements, concentrated during granite crystallization. Others crystallize from hydrothermal fluids or metamorphic processes. People have searched for and treasured these stones throughout history, ascribing mystical properties to them, using them as symbols of status and wealth. But their true wonder is geological. They're samples of extreme conditions, beautiful accidents of chemistry and pressure, preserved across millions of years. Each gemstone is a tiny miracle, a fragment of deep earth made tangible. The power of pressure and heat. Deep within the earth, conditions exceed anything we experience at the surface. Pressure increases about 300 atmospheres per kilometer of depth, reaching millions of atmospheres at the core mantle boundary. Temperature climbs too, reaching thousands of degrees. Under these conditions, matter behaves differently. Minerals stable at the surface break down and reform into denser structures. At about 40 kilometers depth, carbon transforms from graphite to diamond. Olivine, a common mineral in the upper mantle, transforms into denser forms at greater depths, reflecting its atoms' rearrangement into tighter configurations. Water, normally thought of as a surface phenomenon, exists deep in the crust and mantle, locked in mineral structures or dissolved in magma. It plays crucial roles, lowering melting points, facilitating chemical reactions, weakening rocks. The combination of heat and pressure drives metamorphism, transforms rock without melting it, creates new minerals, and ultimately generates magma. These conditions are the engine of geological change, the force behind plate tectonics and mountain building. We can simulate some of these conditions in laboratories, compressing tiny samples and heating them to study how minerals behave. But deep earth remains largely inaccessible, known primarily through indirect methods and rare samples brought up by volcanic processes. The depth where rocks transform. Metamorphism begins at relatively shallow depths, just a few kilometers down, where temperatures reach a couple hundred degrees Celsius. At these low grades, clay minerals and shale begin transforming into harder minerals. As depth and temperature increase, transformations become more dramatic. By 20 kilometers, temperatures approach 500 degrees. Rocks recrystallize, forming new mineral assemblages. Original textures may be erased entirely. Foliation develops as minerals align in response to directional pressure. By 30 kilometers, conditions are extreme. Temperatures near 700 degrees, pressures of 10,000 atmospheres. Rocks from the original surface can barely be recognized. Their chemistry remains similar, but their mineralogy and structure have completely changed. At 40 to 50 kilometers, approaching the upper mantle, some rocks begin to partially melt. This partial melting generates the magmas that feed volcanoes at subduction zones. The deepest metamorphism occurs when oceanic crust is dragged down subduction zones, reaching depths of 100 kilometers or more, before being either melted or incorporated into the mantle. Occasionally, these ultra-high-pressure rocks return to the surface through tectonic uplift, carrying diamonds and other minerals that formed in the deep earth. Evidence of extraordinary journeys through the planet's interior. The formation of coal and oil. Not all rocks are purely mineral. Some preserve organic material, the concentrated remains of ancient life. Coal forms from plant material, accumulated in swamps and bogs, buried before it can fully decay. Over time, pressure from overlying sediment and gentle heating drive off water and volatile compounds, concentrating carbon. Peat becomes lignite, then bituminous coal, and with enough heat and pressure, anthracite, nearly pure carbon. Coal deposits mark ancient wetlands, where forests thrived, sometimes for millions of years, their remains compressing into energy-dense rock. Oil and natural gas formed differently, primarily from marine microorganisms, algae, plankton, bacteria, that settled on seafloors and were buried by sediment. Given the right conditions of temperature and pressure over millions of years, organic molecules break down and recombine into hydrocarbons. These liquid and gaseous molecules migrate through porous rock until trapped by impermeable layers, accumulating in reservoirs we tap for energy. Both coal and oil are fossil fuels, literally fossilized solar energy, captured by ancient photosynthesis and preserved in geological storage. They're finite resources, formed over vast spans of time, which we're consuming in mere centuries. They're also libraries of ancient life, containing molecular signatures of organisms long extinct. The remains of ancient forests. Walk through a coal seam, and you're treading on compressed forest, trees that grew during the Carboniferous period, 300 million years ago, when much of the coal we burn today formed. These weren't forests like we know them. The trees were giant ferns, club mosses, and horsetails, some reaching 30 meters tall. They grew in vast swamps, covering what is now North America and Europe. When they died, they fell into oxygen-poor water, where decay was slow. Layer upon layer accumulated over millions of years, building deposits tens of meters thick. Then tectonic shifts buried these deposits under sediment. Heat and pressure did their slow work, transforming plant tissue into coal. Sometimes you can see the plant origins, impressions of bark or fossilized trunks embedded in the coal. These Carboniferous forests dramatically changed Earth's atmosphere, pulling carbon dioxide from the air through photosynthesis faster than decomposition could return it. Oxygen levels rose. Carbon was locked underground. The climate cooled, eventually triggering an ice age. Those ancient forests, now burned for power, are returning their stored carbon to the atmosphere, reversing in centuries what took millions of years to sequester. The coal we burn is organic, a biological rock, a fossil ecosystem compressed into black stone. The imprints of prehistoric oceans. Ancient seas left signatures in stone. Limestone, formed largely from marine organisms, is one of the most common sedimentary rocks. It's made mostly of calcite, calcium carbonate, either precipitated chemically or accumulated from shells and skeletons. Massive limestone formations indicate warm, shallow seas teeming with life. Chalk is a particularly fine-grained limestone, made almost entirely of microscopic shells from single-celled algae called coccolithophores. The white cliffs of Dover are chalk, hundreds of meters of tiny fossils accumulated over millions of years on the floor of a shallow Cretaceous sea. Chert and flint, found in many limestone formations, formed from the silica skeletons of radiolarians and sponges. Salt deposits mark evaporated seas, where arid conditions concentrated dissolved minerals until they precipitated. Some salt beds are kilometers thick, representing repeated cycles of flooding and evaporation. Black shales rich in organic matter indicate oxygen-poor deep ocean conditions where life thrived in surface waters, but remains accumulated without decay below. Each of these rocks is a portrait of vanished oceans, preserving not just the fact that water once covered the land, but details of depth, temperature, chemistry, and life. The seas have advanced and retreated countless times across continents throughout Earth's history. The fossilized creatures of stone. Some fossils are so detailed they preserve not just bones but soft tissues, feathers, or even the contents of digestive systems. These exceptional fossils, from sites called Lagerstätten, provide extraordinary windows into ancient life. The Burgess Shale in Canada preserves soft-bodied creatures from 500 million years ago in exquisite detail. Animals with body plans, unlike anything alive today, experiments in multicellular life from evolution's early creative burst. The Solnhofen limestone in Germany captured Jurassic marine life, and the earliest known bird, Archaeopteryx, with feathers clearly visible in stone. China's Liaoning province has yielded feathered dinosaurs, showing that feathers evolved before flight. Amber preserves insects and other small organisms in 3 dimensions, sometimes with color retained. Tar pits trapped mammals during the Ice Age, preserving dire wolves, saber-toothed cats, and mammoths. Each exceptional fossil site reveals details impossible to glean from typical fossils: how animals moved, what they ate, how they interacted. They're time capsules of such fidelity that scientists can study ancient muscles, stomach contents, even coloration patterns. These fossils remind us that the past wasn't abstract. Real creatures move through real environments, and occasionally, perfect preservation allows us to meet them across hundreds of millions of years. The layers that record time. Stratigraphy, the study of rock layers, is fundamental to understanding Earth's history. Each layer represents a slice of time, and the sequence of layers is a chronology. But reading this chronology requires care. Layers can be disturbed, folded, overturned, or eroded. Intrusions of igneous rock cut across older layers, providing relative age relationships. By correlating distinctive layers across wide areas, geologists piece together regional and even global histories. Certain layers are particularly useful. Ash beds from massive eruptions spread over vast areas in geologically instant events, creating time markers. Layers rich in the element iridium mark the asteroid impact that ended the Cretaceous period, found worldwide at precisely the same point in the sedimentary sequence. Magnetic reversals recorded in iron-bearing minerals provide another correlation tool. Earth's magnetic field flips irregularly, and these flips are recorded globally. By combining evidence from fossils, radiometric dates, magnetic signatures, and rock types, geologists have constructed a detailed geological timescale spanning Earth's entire history. This timescale divides deep time into eons, eras, periods, and epochs, each defined by distinctive rock layers and fossil assemblages. The layers are more than just rock, their history made tangible, a record written over billions of years. The dating of Earth's deep past. For most of human history, Earth's age was unknown. Some thought it merely thousands of years old. In the 1800s, geologists recognized it must be ancient, but lacked methods to measure age numerically. The discovery of radioactivity changed everything. Certain isotopes decay at known, constant rates, transforming into different elements over time. By measuring the ratio of parent isotope to daughter product in a rock, scientists can calculate how long the decay has proceeded, the rock's age. Different isotope systems work for different timescales. Carbon-14 dating works for organic material up to 50,000 years old. Uranium lead dating can measure billions of years and is used for Earth's oldest rocks. Potassium-argon dating works well for volcanic rocks, millions to billions of years old. Each system has requirements and limitations, but together they provide a powerful toolkit. The oldest terrestrial rocks are about 4 billion years old, found in northwestern Canada. Zircon crystals from Australia are even older, 4.4 billion years, though the rocks containing them are younger. Meteorites, remnants from the solar system's formation, give us the age of the Earth itself, 4.54 billion years. These radiometric dates have revealed the true depth of geological time, transforming our understanding of planetary history. The age of rocks and the clock of decay. Radioactive decay is perfectly suited for geological dating because it's unaffected by temperature, pressure, or chemistry. Only time. When a mineral crystallizes from magma or during metamorphism, it incorporates certain elements. If some are radioactive, they begin decaying immediately. The half-life, the time it takes for half the parent isotope to decay, varies by element. Uranium-238 has a half-life of 4.5 billion years, nearly the age of Earth. With each half-life, half the remaining parent atoms decay. After one half-life, 50% remains. After 25%, the decay is exponential, mathematically predictable. Measuring both parent and daughter isotopes in a mineral reveals how many half-lives have passed. Different minerals in the same rock can be dated independently, providing internal consistency checks. Dating isn't perfect. Metamorphism can reset some isotopic clocks by allowing isotopes to migrate. Weathering can remove or add elements. Careful selection of samples and sophisticated analytical techniques minimize these issues. The result is a detailed chronology of Earth's history, from the formation of the first crust to recent volcanic eruptions. Radiometric dating has revealed not just Earth's age, but the timing of major events. When mountains rose, when oceans opened, when life evolved. It's given geology a precise clock after generations of relative dating alone. The billion-year story beneath our feet. 4.5 billion years is an almost incomprehensible span to grasp it. Imagine Earth's history compressed into a single year. The planet forms on January 1st. The first life appears in March. Complex multicellular organisms don't emerge until November. Dinosaurs appear in mid-December and go extinct on December 26th. Modern humans show up on December 31st at about 11:45 p.m. All of recorded history occupies the final seconds before midnight. This perspective reveals just how recent we are and how patient geological processes are. The rocks beneath us have been cycling through creation and destruction for billions of years. The oldest continental cores, the cratons, have persisted for 3 billion years, though constantly modified at their edges. The ocean floors are young by comparison, none older than 200 million years, constantly recycling. Mountains that seem eternal are temporary. They'll be worn flat eventually and replaced by others. Continents drift continuously, never stationary. The rock beneath your feet right now may have been ocean floor or deep crust or volcanic rock in its past. Over geological time, everything moves, everything changes. The solid Earth is fluid on these timescales. Understanding this deep history fundamentally changes how we see the world. The forces that shape the surface. While tectonic forces build mountains and continents, surface processes constantly work to level them. Erosion, driven ultimately by solar energy and gravity, attacks every elevated surface. Water is the primary agent, rain falling, rivers flowing, waves crashing. Each raindrop loosens a tiny bit of soil. Each river carries sediment toward the sea. The faster the water flows, the larger the particles it can transport. Mountain streams roll boulders during floods. Lowland rivers carry sand and mud. Chemical weathering works more slowly. Acidic water dissolves minerals. Weak acids from decaying plants break down rock. Oxidation rusts iron-bearing minerals. Physical weathering happens through temperature changes, frost action, and crystal growth in cracks. Wind, though weaker than water, sculpts deserts and can transport fine particles across oceans. Glaciers, where they exist, are even more powerful than rivers, grinding rock to powder and transporting enormous blocks. Living things contribute. Plant roots split rock, animals burrow, microbes produce acids and enzymes. All these processes work together, attacking any surface above sea level, gradually wearing it down. The battle between uplift and erosion never ends, creating the dynamic landscape we see. Young mountains standing high, old mountains worn low, plains blanketed with eroded sediment. The slow work of wind and rain. Stand in a desert and watch wind sculpt sand into dunes, constant motion driven by invisible air currents. The wind sorts particles by size. Fine dust travels farthest, sometimes crossing continents. Sand grains hop along the surface in a process called saltation, gradually abrading any rock they encounter. Wind-carved rocks in deserts show smooth, flowing forms, shaped grain by grain over centuries. Rain, though it falls drop by drop, is persistent. Over years, it carves channels. Over millennia, those channels become valleys. Rainwater is slightly acidic, enough to slowly dissolve limestone and other soluble rocks. In humid climates, this creates karst landscapes of sinkholes and caves. Tropical rainforests experience such intense weathering that the soil, despite abundant vegetation, is often thin and nutrient poor. Minerals dissolve and wash away faster than they can accumulate. Freeze-thaw cycles are particularly effective at breaking rock. Water seeps into cracks, freezes, and expands with enormous force, wedging the crack wider. After thousands of cycles, solid rock disintegrates into fragments. Combined, wind and rain are patient sculptors, working on every exposed surface, grinding mountains into sand, one grain at a time, across spans of time that dwarf human civilizations. The carving of canyons and valleys. Rivers are remarkable sculptors. The Grand Canyon, carved by the Colorado River, reveals 2 billion years of geological history in its walls, a vertical mile of layers, each telling part of Earth's story. The carving took about 5 to 6 million years, which seems long until you consider the result. A chasm 400 kilometers long, up to 29 kilometers wide, cutting through some of the hardest rocks on the continent. Rivers don't just flow over landscapes, they create them. Water follows gravity, finding the lowest path. As it flows, it carries sediment that acts as cutting tools, abrading the riverbed. Faster current means more cutting power. During floods, rivers transport enormous loads of sediment and can carve dramatically. Over time, a stream cuts downward, deepening its valley. Tributaries develop, creating branching networks that drain entire regions. Valleys widen as erosion attacks their sides. Meanders form and migrate, snaking across floodplains. When tectonic uplift raises the land, rivers cut down more vigorously, creating steep-walled canyons. The shapes of valleys reveal their history. V-shaped valleys indicate active cutting. U-shaped valleys show glacial modification. Every river is both destroying old landscape and creating new deposits downstream, constantly reworking the surface. The flow of rivers through stone. Watch a river, and you're seeing rock in transit. The sediment flowing downstream was once mountain. It's being delivered to the sea, where it will eventually become new rock. Rivers transport material in 3 ways. Dissolved minerals invisible in the water. Fine sediment suspended in the flow, making the water turbid, and coarse material bouncing or rolling along the bed. A river's transport capacity depends on its velocity. Faster water can carry larger particles. During floods, normally sluggish rivers become powerful, moving material that sits unmoved the rest of the year. Over a river's length, it sorts sediment by size. Boulders dropped early, where gradient flattens, sand carried further, finest clay reaching the sea. This sorting creates distinctive depositional environments, alluvial fans at mountain fronts, braided channels in valleys, meandering rivers across plains, deltas at coasts. Ancient river deposits, now turned to rock, show these same patterns, allowing geologists to reconstruct vanished rivers from hundreds of millions of years ago. Some sedimentary formations contain minerals that could only have come from mountains long since eroded away, their former existence proved by the debris they left behind. Rivers connect highlands to lowlands, moving Earth's surface materials from one place to another in an endless cycle. The desert landscapes of erosion. Deserts reveal erosion's work starkly. Little vegetation obscures the rock, and processes operate at visible timescales. Flash floods, though rare, are powerful sculptors, rushing through normally dry channels and carrying tremendous sediment loads. Wind becomes dominant in the absence of water, piling sand into dunes that migrate slowly across the landscape. Some dunes are enormous, reaching 200 meters high, advancing meter by meter, burying everything in their path. Desert rocks often show remarkable features. Ventifacts are stones carved by wind-blown sand into aerodynamic shapes. Desert varnish, thin dark coatings of manganese and iron oxides, develops on exposed surfaces over thousands of years, created by microbes and chemical reactions. Rocks in deserts undergo thermal stress, heating during the day, cooling at night, which causes expansion and contraction that eventually cracks them. In many deserts, ancient water erosion is visible, channels that haven't flowed in millennia, evidence of wetter climates in the past. Playas, flat-floored dry lakes, accumulate fine sediment and evaporite minerals. The landscapes seem timeless and static, but they're actively changing, just more slowly and episodically than humid regions. Deserts are natural museums, where erosional processes stand exposed to view. The frozen power of glaciers. Glaciers are rivers of ice, flowing under their own weight, sculpting landscapes with tremendous power. When snow accumulates faster than it melts, it compresses into ice. As the ice thickens, pressure causes it to deform and flow downhill like an extremely slow fluid. Alpine glaciers flow through mountain valleys, while continental ice sheets can cover entire regions. The base of a glacier, where ice meets rock, is where erosion happens. Rock fragments frozen into the ice act as cutting tools, grinding the bedrock smooth. Glaciers pluck blocks from bedrock, incorporating them into the flowing ice. The result is distinctive erosion, U-shaped valleys, where glaciers widened, former stream valleys, cirques carved into mountainsides, polished bedrock surfaces with long scratches called striations. Glaciers transport enormous amounts of material, from fine powder to house-sized boulders. When ice melts, this material is deposited as moraines, till, and outwash. Glacial landscapes have a distinctive look even millions of years after the ice is gone. During ice ages, glaciers covered much larger areas than they do today. In North America, ice extended as far south as New York and the Midwest. The Great Lakes were carved by glaciers, as were countless smaller lakes, valleys, and landforms across northern latitudes. The sculpting of mountains by ice. Mountains above the snow line experience continual glacial modification. Snow accumulates in high basins, compressing into ice, flowing downhill as glaciers. These rivers of ice carve distinctive features. Cirques are semicircular basins with steep walls, formed where glaciers eroded into mountainsides. Multiple cirques on a single mountain create sharp ridges called arêtes and pointed peaks called horns. The Matterhorn is the classic example. Glaciers flowing down valleys widen and deepen them, transforming V-shaped stream valleys into U-shaped glacial valleys with steep walls and flat floors. Hanging valleys form where smaller tributary glaciers join the main glacier. When the ice melts, these tributaries are left high on the valley walls, often marked by waterfalls. Fjords are drowned glacial valleys, carved below sea level, then flooded when ice melted and sea level rose. The sheer scale of glacial erosion is impressive. Valleys excavated hundreds of meters deep, mountains carved into dramatic spires and ridges. This sculpting continues wherever glaciers exist, though most alpine glaciers are currently retreating due to warming climate. The landscapes they created remain as evidence of ice ages past, showing just how dramatically climate shifts can reshape terrain through the advance and retreat of ice. The traces of ancient ice ages. Earth has experienced numerous ice ages, periods of extensive glaciation, lasting millions of years, with shorter glacial and interglacial periods within them. We're currently in an interglacial period within an ice age that began about 2.6 million years ago. Evidence of ancient glaciations appears in the rock record. Glacial till, unsorted sediment, deposited by melting ice, forms distinctive deposits. Striations on bedrock show ice flow direction. Erratics, boulders carried far from their source and left when ice melted, appear out of place in the landscape. Dropstones in marine sediments indicate icebergs melting while drifting, dropping their rocky cargo into seafloor mud. The oldest known ice age occurred about 2.4 billion years ago. Another major glaciation happened around 700 million years ago, possibly a snowball Earth event when ice may have covered the entire planet. Ice ages correlate with various factors: continental positions affecting ocean currents, atmospheric carbon dioxide levels, orbital variations. Each glaciation leaves traces in the geological record, evidence of dramatically different climate conditions. Studying these ancient ice ages helps us understand Earth's climate system and how it can shift between radically different states over geological time. The patterns suggest climate is sensitive to relatively small changes in conditions, capable of dramatic swings that reshape entire continents under ice. The evidence found in rock strata. Every layer of sedimentary rock contains clues about the conditions when it formed. Grain size indicates energy levels. Coarse grains mean strong currents. Fine grains suggest calm water. Sedimentary structures tell stories too. Ripple marks preserved in ancient sandstone show current direction. Mud cracks indicate periodic drying. Cross-bedding reveals how sand dunes or underwater currents moved. The presence of certain minerals indicates climate. Evaporites form in arid conditions. Coal in wet tropical environments. Fossils within layers reveal not just what organisms lived, but also environmental conditions. Coral fossils indicate shallow tropical seas. Fern fossils suggest humid forests. The color of sedimentary rock provides information. Red beds form in oxidizing conditions. Black shales in oxygen-poor environments. By reading these signs, geologists reconstruct ancient environments with remarkable detail. A sequence might show beach sand overlain by shallow marine limestone, then deep ocean shale, recording a transgression as sea level rose and water deepened. Another sequence might show river deposits topped by volcanic ash, documenting a landscape suddenly buried by eruption. Each layer is a page in Earth's history book, recording not just time passing, but specific conditions and events. The climate, written in sediment. Climate leaves signatures in sediment that persist as rock. Glacial deposits indicate cold periods. Unsorted till, striated stones. Dropstones in marine sediments. Desert sandstones with large-scale cross-bedding mark arid climates. Thick coal seams indicate warm, wet conditions supporting lush vegetation. Evaporites, rock salt, gypsum, form where evaporation exceeds precipitation. Laterite soils, rich in iron and aluminum, develop in tropical climates with intense weathering. By mapping where these climate indicators appear in rocks of the same age, geologists reconstruct ancient climate zones. Sometimes they find puzzling distributions: glacial deposits in rocks now located at the equator, coal beds in rocks from polar regions. These anomalies helped confirm continental drift. The rocks hadn't formed in strange climates. They'd formed in appropriate climates, then drifted to new latitudes over millions of years. Oxygen isotope ratios in marine fossils record ancient ocean temperatures. Pollen preserved in sediments reveals past vegetation. Ice cores from Greenland and Antarctica contain bubbles of ancient atmosphere, direct samples of air from hundreds of thousands of years ago. Together, these climate proxies allow reconstruction of Earth's climate history, revealing a dynamic system that has shifted dramatically over time. The ocean floors beneath the waves, the seafloor, covering 70% of Earth's surface, was almost entirely unknown until the mid-20th century. Early depth soundings suggested vast, flat plains, but detailed mapping revealed spectacular topography: mountain ranges taller than the Himalayas, trenches deeper than mountains are high, volcanic chains, fracture zones, and plateaus. The mid-ocean ridge system is Earth's longest mountain range, running continuously for 60,000 kilometers through all ocean basins. These ridges mark divergent plate boundaries where new seafloor forms. They rise 2 to 3 kilometers above the surrounding seafloor, with a rift valley at their crest. As newly formed crust moves away from the ridge, it cools, contracts, and sinks, creating the characteristic depth profile of ocean basins: shallowest at ridges, deepest near the edges. Abyssal plains, the flattest surfaces on Earth, cover much of the deep ocean floor, blanketed by fine sediment accumulated over millions of years. Seamounts, underwater volcanic mountains, number in the tens of thousands, some arranged in chains recording the path of tectonic plates over mantle hotspots. The seafloor is young, constantly recycled, yet it's also a vast archive of Earth's recent history. The mid-ocean ridges and trenches. Mid-ocean ridges are where Earth's crust is born. Tectonic plates pull apart, pressure drops, and mantle rock partially melts. The resulting magma rises, erupts underwater, and cools into new basaltic crust. This process, called seafloor spreading, creates new ocean floor continuously. The ridges aren't straight. They're offset by transformed faults perpendicular to spreading direction. Mapping these features helped confirm plate tectonics theory. At the opposite end of the cycle are trenches, where oceanic crust returns to the mantle. These are Earth's deepest places. Narrow depressions, where one tectonic plate bends and descends beneath another. The Mariana Trench reaches nearly 11 kilometers deep. Conditions at such depths are extreme. Pressures exceed 1,000 atmospheres. Temperatures near freezing. Complete darkness. Yet life exists, even here. Trenches are sites of intense geological activity. As the descending plate is dragged deeper, increasing temperature and pressure release water from minerals. This water rises into the overlying mantle, lowering its melting point and generating magma that feeds volcanic arcs, chains of volcanoes parallel to trenches. The Pacific Ring of Fire, with its frequent earthquakes and eruptions, outlines subduction zones encircling the Pacific Ocean. Ridges create, trenches destroy. Together they recycle the ocean floor. The movement of seafloor spreading. Seafloor spreading was a revolutionary idea when proposed in the 1960s. If new crust forms at ridges and the Earth isn't expanding, old crust must be destroyed elsewhere. At trenches, several lines of evidence confirmed this. Seafloor age increases with distance from ridges. As predicted, the pattern is symmetrical on both sides of ridges. Magnetic stripes in the basalt run parallel to ridges. As magma cooled, iron minerals aligned with Earth's magnetic field, recording its direction. Because Earth's field reverses irregularly, the seafloor displays a striped pattern of normal and reversed magnetism, symmetrical across ridges and wider in faster spreading areas. This pattern provided powerful evidence for spreading. Heat flow measurements showed ridges are hot, trenches cooler. Sediment thickness increases away from ridges. The older the crust, the more time for sediment to accumulate. Ocean drilling confirmed these patterns. Retrieving cores showing progressive age increases with distance from ridges. The spreading rates vary. The East Pacific rise spreads about 15 centimeters per year. The Mid-Atlantic ridge, only 2 to 3 centimeters annually. These rates explain why the Pacific is shrinking while the Atlantic grows. Seafloor spreading is the mechanism driving plate tectonics, powered by mantle convection. The hidden volcanoes under the sea. Most volcanic activity on Earth happens underwater, unseen by human eyes. The mid-ocean ridge system is essentially a continuous volcanic feature, erupting regularly but rarely observed. These eruptions build the ocean floor, but because they're underwater and often deep, they rarely make news. Only occasionally does a ridge eruption create enough lava to build an island, like Surtsey off Iceland in 1963, a mountain born from the sea in spectacular fashion. Beyond the ridges, thousands of seamounts dot the ocean floor, extinct or dormant volcanoes rising from the depths. Some reach close to the surface, but never breach it. Others once formed islands, but have since subsided and eroded below sea level, crowned with coral reefs that became atolls as the volcanic base sank. Guyats are flat-topped seamounts, their summits planed flat by wave action when they were islands, then carried by plate motion into deeper water. Underwater eruptions create unique lava forms. Pillow basalts formed when lava chills instantly in contact with cold water. Hydrothermal vents at seafloor, spreading centers spew mineral-rich hot water, creating chimney-like structures and supporting exotic ecosystems based on chemical energy rather than sunlight. These hidden volcanoes play crucial roles in ocean chemistry, heat distribution, and marine life. The basalt plains of the deep earth. Basalt forms the foundation of all ocean basins. Dark, fine-grained rock, rich in iron and magnesium, erupted at mid-ocean ridges and cooled rapidly in seawater. This rock type covers more of Earth's surface than any other, though most lies hidden beneath ocean waters. Oceanic basalt is remarkably uniform in composition compared to continental rocks, reflecting its direct origin from mantle melting. It's also young. No oceanic crust older than about 200 million years exists, all older material having been recycled into the mantle at subduction zones. Continental rocks, in contrast, can be billions of years old. The ocean floor consists of distinct layers. At the top is a thin veneer of sediment, thickening with distance from ridges. Below that, pillow basalts from underwater eruptions. Deeper, a layer of vertical dikes, magma, that fed the surface eruptions. Below that, gabbro, coarse-grained rock, with the same composition as basalt, but cooled slowly underground. This layered structure, called ophiolite, when found on land, represents slivers of ocean floor thrust onto continents during collisions. Basaltic crust is denser than continental crust, which is why it subducts, while continents float. The composition and structure of ocean basalt tells us about mantle processes occurring beneath the ridges, the magnetic patterns in ocean rocks. One of the most beautiful conformations of seafloor spreading comes from magnetic stripes on the ocean floor. As basaltic lava erupts and cools, at mid-ocean ridges, iron-bearing minerals crystallize and align with Earth's magnetic field like tiny compass needles frozen in place. The rock remembers the field direction at the time it formed. Earth's magnetic field isn't constant. Every few 100,000 years on average, the poles flip. North becomes south, south becomes north. The mechanism isn't fully understood, but the record is clear in rocks of different ages. When scientists mapped the magnetic properties of seafloor rocks, they discovered alternating stripes of normal and reversed polarity running parallel to spreading ridges. The pattern is symmetrical. The same sequence of reversals appears on both sides of the ridge, progressively older with increasing distance. The stripe widths vary based on spreading rate. and how long each polarity lasted. This pattern could only form if new crust continuously forms at ridges and spreads symmetrically away. The magnetic stripes are a recording of Earth's magnetic field history, written in stone as the ocean floor was created. They provided some of the most convincing evidence for plate tectonics and seafloor spreading. The minerals that build our world. Human civilization is built on geology. Every structure requires materials extracted from Earth: stone for buildings, metals for tools and machines, minerals for electronics, fuels for energy. Ancient peoples used flint for tools, clay for pottery, copper and tin to make bronze. The Iron Age brought stronger metals. Modern technology depends on dozens of elements: silicon for computer chips, rare earths for magnets and displays, lithium for batteries, platinum for catalysts. These don't exist freely in nature. They must be found concentrated in ore deposits, mined, processed, refined. Ore formation is a geological process requiring specific conditions to concentrate elements from trace amounts dispersed in rocks to economically viable deposits. Hydrothermal fluids dissolve and transport metals, depositing them in veins. Magmatic processes concentrate valuable minerals. Weathering can form residual deposits as less valuable minerals dissolve away. Sedimentary processes create placer deposit where dense minerals accumulate. Finding these deposits requires understanding geology, knowing what processes concentrate which elements, recognizing indicator minerals, interpreting structures. Mining has driven exploration and geological understanding throughout history. The minerals we extract represent geological processes operating over millions of years, concentrated by chance into deposits we can exploit. Every metal object, every electronic device traces back to the rocks. The use of stone in human history. Stone was humanity's first technology. Sharp-edged flakes for cutting, hammers for processing food and materials, eventually shaped tools for specialized purposes. Early humans selected stone carefully, seeking types that flaked predictably: flint, chert, obsidian. Quarries appeared where good tool stone was abundant, and trade networks distributed it across vast distances. As civilizations developed, stone became architecture. Limestone, easy to cut and shape, built the Egyptian pyramids, structures so massive they'll outlast most modern buildings. Marble, metamorphosed limestone, prized for its beauty, became sculpture and monuments. Granite, hard and durable, formed temple columns and foundations. The Romans used volcanic tuff and developed concrete from lime and volcanic ash, creating structures like the Pantheon that still stand 2,000 years later. Medieval cathedrals rose from quarried limestone. Entire mountains transformed into soaring architecture. Slate roofs, sandstone walls, marble floors. Buildings were made from the local geology. Even today, though steel and concrete dominate, stone remains important. Dimension stone for facades and countertops, crushed rock for roads and concrete aggregate, gravel for drainage. The very ground we live on becomes the materials we build with, a direct connection between geology and civilization. The quarries and the tools of time. Quarries are geological wounds, places where humans have excavated rock in quantity. Some are ancient, worked intermittently for thousands of years. Others are modern industrial operations, moving millions of tons annually. Walking through a quarry, you see geology exposed in 3 dimensions: layers, faults, intrusions, all visible on massive scales. Quarrymen develop deep practical knowledge of stone, understanding how it breaks, which directions it splits most easily, how to extract blocks without shattering them. Different stones required different techniques. Limestone could be sawed. Granite required drilling and wedging, exploiting natural fracture planes. Marble was extracted in enormous blocks, valuable enough to justify careful, slow work. The tools evolved with technology. Ancient quarries show marks from bronze and iron tools, holes drilled with simple bow drills using sand as abrasive. Medieval quarries employed water-filled holes that froze in winter, expanding ice, fracturing the rock. Modern quarries use diamond-tipped saws, explosives, heavy machinery, but the principle remains: finding valuable stone and removing it from its natural setting. Abandoned quarries often fill with water, creating artificial lakes, or become geological study sites where rock is spectacularly exposed. They're monuments to the human need for stone, showing how deeply we've mined the Earth's crust. The cathedrals built from the earth. Medieval cathedrals are geology-made architecture. Each stone in their walls began as sediment, accumulating on ancient seafloors, compressed into rock, uplifted by tectonic forces, exposed by erosion, then quarried and shaped by human hands. The great European cathedrals used local stone. Limestone was most common, workable yet durable. Builders understood stone properties intuitively. They knew which layers split easily, which were strong, which weathered well. Sometimes multiple stone types appear in a single building, as builders exhausted nearby quarries and sourced from farther away. Fossils are common in cathedral stones. You can spot ancient sea creatures in walls, hundreds of meters tall. The buildings themselves are now weathering, returning slowly to sediment. Acid rain, pollution, and time erode the carved details, requiring constant restoration. In a sense, these structures are temporary, just longer lasting than most human creations. They represent a moment when rock was shaped to human purpose before eventually returning to the geological cycle. The stone will outlast the civilization that carved it, but eventually even the pyramids will wear away, their materials dispersed by erosion, perhaps to be incorporated into future sediments, compressed into new rock, completing another cycle through deep time. The modern science of geology. Today's geology combines field observation with sophisticated technology. Geologists still examine rocks with hand lenses, map formations, collect samples. Direct observation remains fundamental, but now they augment this with powerful tools. Seismology reveals Earth's interior structure by analyzing how waves from earthquakes travel through the planet. GPS tracks plate motions in real time, measuring movements of millimeters per year. Satellites image the surface at multiple wavelengths, detecting minerals, moisture, and subtle topographic changes. Geochemical analysis determines rock composition and age with precision. Computer models simulate tectonic processes, mantle convection, and climate over millions of years. Drilling projects penetrate kilometers into the crust, retrieving cores from environments never directly sampled. Ocean floor mapping uses sonar to create detailed bathymetric maps. Experimental geology subjects rocks to extreme pressures and temperatures in laboratories, replicating deep Earth conditions. The science has expanded from describing what rocks look like to understanding the processes that form them, the forces that move continents, the cycles that operate over billions of years. Yet the fundamental questions remain, those that have always driven geology. How did Earth form? How does it work? How has it changed? How will it continue to change? The satellites that map the planet. From orbit, satellites observe Earth with instruments humans could never carry on the ground. Optical sensors capture images showing geological features, faults, folds, erosion patterns, visible from space. Radar penetrates clouds and vegetation, revealing topography and even subsurface structures in deserts. Infrared detects heat, useful for monitoring volcanoes and finding hydrothermal activity. Multispectral imaging identifies minerals by their characteristic reflections at different wavelengths, mapping rock types across vast areas. GPS and other positioning systems reveal ground movement with millimeter precision, tracking the slow creep of tectonic plates, the swelling of magma beneath volcanoes, the subsidence of areas where groundwater is extracted. Gravity measurements from orbit map density variations in the crust and mantle, revealing buried structures and composition changes. Magnetic field satellites detect anomalies that indicate ore deposits or geological structures. The continuous observations build databases spanning decades, showing changes over time: glaciers retreating, deserts expanding, volcanic eruptions, earthquake damage. This orbital perspective revolutionized geology, providing global coverage and perspectives impossible from the ground. Features that seemed random on the ground reveal patterns from space. Geology became a planetary science, understanding Earth as a whole system observed from outside. The exploration beneath the surface. We've barely scratched Earth's surface. The deepest mine extends about 4 kilometers down. The deepest drill hole, the Kola superdeep borehole in Russia, reached just over 12 kilometers before stopping, still within the crust. The mantle, beginning 30 to 70 kilometers down, has never been directly sampled, except where tectonic forces have thrust pieces to the surface. The core is known only through indirect methods, yet geologists continue pushing deeper. Ocean drilling projects sample seafloor sediments and basalt, reconstructing millions of years of Earth history. Scientific drilling on land penetrates fault zones, volcanic systems, and ancient impact craters. Each project recovers cores, cylinders of rock brought from depths that are analyzed for composition, structure, age, and contained fluids. The temperatures and pressures increase rapidly with depth, making drilling technically challenging, but each meter deeper brings new information about how Earth's interior works. Future projects aim to drill through oceanic crust into the mantle. The Malhole project, attempted in the 1960s and still unrealized. Despite technological advances, Earth's interior remains largely inaccessible, known primarily through indirect methods: seismology, gravity, magnetism, and computer modeling. Direct exploration is limited, making every sample from depth precious. The study of earthquakes and hazards. Geology isn't just about understanding the past. It's about assessing present hazards and predicting future risks. Earthquakes, volcanic eruptions, landslides, tsunamis, all are geological phenomena that threaten human populations. Geologists map fault locations, study their history, and estimate recurrence intervals for major earthquakes. They monitor volcanoes for signs of impending eruptions, ground swelling, increased seismicity, gas emissions. They assess landslide susceptibility based on slope, rock type, and precipitation patterns. This information informs building codes, land use planning, and emergency preparedness. After disasters, geologists investigate to understand what happened and improve future predictions. The science is imperfect. Earthquakes remain unpredictable beyond probabilistic assessments, but knowledge saves lives. Communities in seismically active regions build accordingly. Volcano observatories provide warnings that allow evacuations. Tsunami warning systems detect earthquakes that might generate waves. Understanding geological hazards is crucial for the billions of people living in vulnerable areas. As population grows and climate changes, these hazards may increase. Geology provides the knowledge needed to adapt, to build resilience, to live safely on a dynamic, sometimes dangerous planet. The rocks don't just tell us where we've been, they warn us what might come. The living planet that never stops moving. Earth is alive, not in the biological sense, but geologically. The interior remains hot from formation and radioactive decay. Convection currents churn the mantle, plates drift across the surface, volcanoes erupt, earthquakes shake, mountains rise. This activity has continued for over 4 billion years and will persist for billions more until the interior cools sufficiently for convection to stop. Only then will Earth become truly geologically dead, like the Moon or Mars, its surface frozen in time. But that's far in the future. For now, Earth remains dynamic. The continents continue their slow journey, currently fragmenting the former supercontinent, but eventually assembling into a new one. The ocean floor recycles every 200 million years. Mountains rise and erode away on similar timescales. Climate shifts dramatically over millions of years, driven partly by changing continental positions and ocean circulation. Ice ages come and go. Sea levels rise and fall. Through all this, life adapts or perishes, evolution responding to geological changes. The solid Earth and living biosphere are intimately connected, each influencing the other. Understanding this dynamic system, how it works, how it changes, is geology's ultimate goal. The planet is never static, never finished. It's constantly becoming something new while carrying within it the memory of everything it's been. The endless story, written in the rocks. Every rock has a story. Some are simple. A sandstone formed from beach sand, preserved through burial and cementation. Others are complex. A metamorphic rock that was once sediment, then buried and transformed multiple times. Each event overwriting, but not completely erasing earlier history. Geologists are readers of these stories, translating texture and composition into narratives of deep time. The more you learn to read rocks, the more they reveal. That pebble on the beach. Where did it come from? What rock type is it? How did it get rounded? How far did it travel? Each question opens into deeper inquiry. The cliff face beside the road. What are those layers? What environments do they represent? Why are they tilted? What forces acted on them? Geology trains a way of seeing, recognizing in every landscape the processes that shaped it, and the vast time those processes required. The story written in rocks is the autobiography of Earth itself, a narrative 4.5 billion years in the making, and far from finished. We're privileged to read parts of it, to piece together how this planet formed, evolved, and continues changing. The rocks are patient. They'll outlast us by unimaginable spans. They'll continue telling their stories to whoever comes next, recording everything that happens, adding new chapters to the endless volume of Earth's history.